So in this video, I'm going to introduce acid-base indicators. Now you guys have already used indicators in the lab. And I told you that an indicator is used in order to tell us when the solution is at equivalent number of moles of acid and equivalent number of moles of base. Now let's dive into that a little bit deeper. So I have the definition of an acid-base indicator up here at the top. It's just a weak acid or a weak base that displays different colors for the ionized and the unionized forms. Okay, so acetic acid, for instance, could not work as an indicator because it remains colorless when it's an acidic and mostly acidic compound or mostly basic part of the acetate ion, for instance, hanging out in solution. They're both colorless, so there's no indication of when it goes from an acidic solution to a basic solution. Indicators, however, are great because they do have the different colors for each of them. So let's stick with weak acid for our purposes here, just while we're talking about all of this. The weak acid for the generic indicator, that's the IN part of this equation, for the generic indicator is going to have an equilibrium like this. Now, when the species that is in solution is mostly like this, say it will be a red solution, okay? It will be, if most of the species in solution are in the HIN form, that is the unionized form, right? This is the unionized form of the acid here. Say it's red. Now, if you increase the likelihood that the IN minus will be most likely formed here. Let's say that when IN minus is mostly in solution, it's blue, okay? And the indicator tells us when it switches from red to blue is when you have achieved or gone past equivalent moles of each. So for this generic indicator, when you transition from red to blue, you have gone past the end point, okay? And the end point is essentially, it's essentially how we can determine what the equivalence point is for any titration, okay? The end point is the physical indication where the color changes, and the equivalence point is where the neutralization is complete. So we can use the end point to estimate the equivalence point. Now remember, each weak acid has its own K sub A, right? So any indicator would be useful for only particular titrations. Say, for instance, we want to have an indicator in a titration with a strong acid to a strong base, So for that particular titration, we would need a specific indicator where its K sub A would be about where the strong acid and strong base would have equivalent moles. That is to say, for strong acid and strong base, the pH should be around 7, right? If you have a strong acid being titrated with a strong base. So the K sub A, or excuse me, the pKa needs to be around 7 in order to be a useful indicator for that particular titration. So here is a list of common acid-base indicators and you guys have already seen a couple of these in lab, right? You've used phenolphthalein here when you were doing the titration of acetic acid with NaOH, for instance, and you've also seen methyl orange as well, this guy right here. So the indicator is going to depend on the titration that you're doing, okay? Now the indicator needs to have, its pKa should be close to the pH range that you expect the equivalence point to happen, okay? Now the phenolphthalein, for instance, notice it has a pH range of about 8.3 to 10 here. That means that if we are to use phenolphthalein, we're expecting our titration to also have an equivalence point of within that range, preferably in the middle of this range, right? So say around 9-ish. And that is actually what we do see when we titrate the weak acid, acetic acid with NaOH. And this is because of the steepest part of the titration curve should be equivalent to the equivalence point. And that is to say that the indicator must change color where the titration curve is at its steepest point. So if I knew that I was going to have an equivalence point around 8.5, that is to say I was titrating a weak acid with a strong base, I am aware that the pH should be greater than 7. Okay. Now, if I want to pick an indicator for that particular interaction, I'm going to choose something along the lines that has a higher pH range, because that will tell me when I am going from the unionized, that is to say the HI from the previous slide, the HI will go to the IN minus and will change color in the correct pH range. And I look to the pKa of that particular indicator. And this table right here just shows the pH ranges for these particular indicators. Now, what if I was titrating a strong acid and a weak base? Well, I know that the pH range should be, the equivalence point should be with a pH less than 7. So I would look to these indicators here at the top of this table to have a more acidic pH range. That is to say that the pKa is somewhere more in the acidic range. It needs to be more of an acidic solution in order to have majority HI converted to I minus. Now, what if I wanted to do the strong acid and strong base? As I've already kind of mentioned, the pH will be around 7, right, for the equivalence point. So we could actually use quite a wide range of indicators, at least from this table, in order to get us to be a good indication of when we have an equivalence point. So the strong acids and strong bases can actually use any of these indicators here to tell us when we would be able to reach an equivalence point. Now, the reason this is the case is because of the pH range with the strong acid, strong base titration is such that the steep part of the curve is pretty broad, and that allows us to have a little bit of wiggle room in terms of adjusting the pKa or adjusting the indicator to get the correct pH range to where these indicators that I've highlighted here will go from the HI or the unionized form to the I minus or the ionized form of the indicator.